This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion delves into the fascinating world of interactive physics simulations. We'll be exploring a specific tool, the Charge Distribution Simulator, designed to enhance learning in electromagnetism. It's a powerful resource, and our guest is here to shed light on its capabilities.
Indeed. Interactive simulations offer a unique way to bridge the gap between abstract concepts and practical understanding, particularly in a field like electromagnetism, where visualization is key.
Exactly. Many students struggle to visualize electric fields. How does this simulator address that challenge?
It allows students to manipulate variables directly, observing the immediate effects on the electric field. This hands-on approach fosters a deeper, intuitive grasp of the subject matter.
Intriguing. Let's dive into the specifics of the simulator's functionality and its educational applications. The simulator uses HTML5, making it accessible across various platforms. What are some of its key features?
The HTML5 base is crucial for accessibility. Beyond that, the simulator allows users to adjust the charge distribution, specifically the height of an ellipse in this case, and observe the resulting electric field. They can also manipulate the velocity of a charged particle within the field, altering both its magnitude and direction.
So it's not just a static visualization, it's truly interactive. Right, what about visual aids?
Absolutely. The simulator includes options to toggle the visibility of velocity and force vectors, providing a clearer picture of the forces at play. There are also play/pause and reset functionalities for controlled experimentation.
How can educators best utilize this simulator in the classroom?
It's ideal for classroom demonstrations, allowing instructors to illustrate complex concepts in a dynamic and engaging way. Students can also use it for independent exploration and experimentation, completing assignments that require them to manipulate variables and analyze the results.
It sounds like a valuable tool for both teaching and assessment. Are there any limitations?
While the HTML5 format ensures broad accessibility, the underlying easy JavaScript simulations library, EJOS, has licensing restrictions for commercial use. Educators should be aware of this.
The simulator is part of a larger collection of open educational resources, OER, hosted on the Open Educational Resources/open/physics at Singapore website. What's the significance of this?
The OER aspect is vital. It ensures that this valuable educational tool is freely available to educators and students worldwide, promoting inclusivity and accessibility in STEM education. The website itself offers a wealth of similar resources covering various physics and mathematics topics.
That's a significant contribution to the educational landscape. What other simulations are available on that platform?
The website boasts a wide array of simulations covering mechanics, electromagnetism, quantum physics, optics, waves, and more. There's even a selection of mathematics simulations. It's a comprehensive resource.
What areas could benefit from further development or investigation regarding this simulator?
Further investigation into the sample learning goals and research sections would be beneficial. Also, creating video demonstrations showcasing the simulator's capabilities would enhance its usability and appeal. Testing its compatibility and performance across different devices and browsers is also crucial.
And what about the potential for future applications beyond education?
The simulator's embeddable nature makes it suitable for integration into online courses and learning management systems. Its interactive nature could also be adapted for use in other contexts, such as training simulations for professionals working in fields related to electromagnetism.
How does this interactive approach compare to traditional methods of teaching electromagnetism?
Traditional methods often rely heavily on lectures and textbook diagrams, which can be abstract and difficult for some students to grasp. Interactive simulations like this one offer a more engaging and intuitive learning experience, allowing students to actively participate in the learning process.
So it's a more active learning approach. What are the advantages of each method?
Traditional methods provide a structured foundation of theoretical knowledge. Interactive simulations, however, excel at reinforcing that knowledge through hands-on experience and visualization, leading to a deeper and more lasting understanding. A blended approach, combining both, is often the most effective.
Many students struggle with visualizing abstract concepts in physics. How does this simulator help overcome this hurdle?
The interactive nature of the simulator allows students to manipulate variables and see the immediate effects on the electric field. This hands-on approach makes abstract concepts more concrete and easier to understand. It transforms learning from passive observation to active exploration.
Does the simulator provide any feedback mechanisms to help students learn from their mistakes?
While the provided text doesn't explicitly detail feedback mechanisms, the interactive nature of manipulating variables and observing immediate consequences inherently provides a form of feedback. Students can experiment, see the results, and learn from their observations. Further development could incorporate more explicit feedback mechanisms.
What is the overall role of interactive simulations in promoting active learning and student engagement?
Interactive simulations transform passive learning into active engagement. They allow students to explore concepts at their own pace, experiment with different variables, and receive immediate feedback. This active participation fosters deeper understanding and increased retention.
Does this approach cater to different learning styles?
Absolutely. The visual and interactive nature of the simulator caters to visual and kinesthetic learners, while the ability to manipulate variables and analyze results appeals to analytical learners. Its versatility makes it a valuable tool for a diverse student population.
How accessible and usable is the charge distribution simulator?
The HTML5 format ensures broad accessibility across various devices and browsers. The intuitive interface and clear instructions further enhance usability. The availability of translations into other languages further broadens its reach.
Are there any aspects of the user interface that could be improved?
While the current interface seems user-friendly, further development could incorporate more detailed instructions, tutorials, or even interactive help features to guide users through the simulation's functionalities.
You mentioned licensing restrictions for commercial use of the EJS library. Can you elaborate?
The Easy JavaScript Simulations Library, EJS, used to create the simulator has a separate license for commercial use. Educators and individuals using the simulator for non-commercial educational purposes are generally covered under the Creative Commons Attribution Share Alike 4.0 Singapore license. However, commercial use requires reviewing the EJS license and contacting the relevant parties.
So it's important for users to understand the licensing implications before using the simulator in commercial ventures. What are your overall thoughts on the charge distribution simulator and its potential impact on physics education?
The Charge Distribution Simulator is a valuable tool for enhancing the teaching and learning of electromagnetism. Its interactive nature, accessibility, and the wealth of resources available on the Open Educational Resources/Open Source Physics at Singapore website make it a significant contribution to STEM education.
What are some potential future directions for this type of interactive simulation?
Future development could focus on incorporating more sophisticated feedback mechanisms, expanding the range of customizable parameters, and integrating more advanced features such as data logging and analysis tools. The potential for incorporating augmented or virtual reality elements is also exciting.
Let's test our understanding with a quick quiz. What is the primary function of the charge distribution simulator?
To visualize and interact with electric fields generated by charge distributions, specifically a sharp ellipse charge.
How can you adjust the particle's velocity?
By dragging the particle, changing both its magnitude and direction.
And finally, what does toggling the velocity and force checkboxes do?
It makes the velocity and force vectors visible or invisible on the simulation display.
That was a great discussion. Thank you for sharing your expertise on the charge distribution simulator and its potential to revolutionize physics education.